So the first talk of the session will be given by Professor Yuval Gefen from the Weizmann Institute of Science, and he'll talk to us about quantum cooling. I was hoping to see the title over there.
There is a cricket fan club called the Fraternity Hostile. Members of this club cannot really stand each other. So when we put two of them in the same room, they immediately want to leave through opposite doors. However, if we force them to spend some time and interact with each other, then they may start liking each other and live through the same door. So if we replace room by particle collider, doors are drains, and members of the club, you know what kind of particles they are, you get the flavor of what I'm going to tell you about today. Actually, I decided to adapt the topic of my talk, not as announced, to make it more fit to the theme of this conference. I will talk about entanglement of both electrons and anyons. And my collaborators, the theory collaborators on these works are Igor Gorny of Karlsruhe Institute of Technology, Germany, and Gu Zhang of Beijing Academy of Quantum Information, China. So among the various works that we published, two are in collaboration with the experimental groups, with the group of Heiblum and the group of Frederic Pierre. So this is the point to thank Sthitadhi and Subroto and Manas and Subro for inviting me here, and it's a great honor to be the first speaker of this program that is supposed to fuse two major present-day themes in physics: the new generation of many-body physics and platforms of quantum information. Specifically, my talk today will combine three directions of intensive activity. One has to do with entanglement and entanglement entropy and dynamics thereof. The other has to do with the study of quantum statistics of anyons. And the third one is something that emerged over the past 4 years, the study of platforms, experimental and theoretical platforms of particle colliders in low energy particle colliders on the level of condensed matter physics. So I will follow here this line. I will introduce and discuss the notion of entanglement pointers. I will then talk about the study, theory, and experiment of entanglement entropy, and in particular, we'll focus on that part of entanglement entropy that comes from statistics, from quantum statistics. And I will say a few words about the experiment, and as I mentioned before, I will do that both for electrons and for abelian anyons. So a quick reminder of what entanglement entropy is all about. We have a multi-partite system, in this example, a bipartite system comprising parts A and B. Rho is the density matrix of the entire system, but we can define here a reduced density matrix, rho sub A, by integrating out all degrees of freedom associated with the part B. So we can now take this reduced density matrix, which in general will describe a mixed state, not a pure state, and compute the entropy associated with this density matrix. That will be the entanglement entropy. We can follow the definition of von Neumann or of Reni. This is the nth order Reni entropy. This will be the entanglement entropies. So now we come to the platforms we are interested in. But before that, this is the line of thought behind our discussion. So I will be interested in measuring entanglement entropy for various electronic and anionic platforms. What is special about these platforms is that these are platforms that support quantum transport. So leaving aside full counting statistics, which is not easily accessible, this is the first time, both theoretically and experimentally, such a derivation of entanglement entropy becomes possible when we talk about not stationary systems, but systems that actually conduct current, quantum systems that conduct current. And as I said before, I will focus in this system on the derivation of entanglement entropy, which is associated with quantum statistics. So this is a schematic view of the experimental setup. This is the electron microscopy of the same system. So we have here a source SA, giving rise to a continuous beam of particles. Most of these particles are now collected in the drain dA tilde, but a small part of the particles manage to tunnel in this direction. This is will be a dilute beam, and this dilute beam meets another dilute beam coming from the source SB. They collide here, and as a result, the outgoing particles are collected in the drain dA and dB. And this system is clearly bipartite. A theorist view of the system is shown here. We have a continuous noiseless beam coming out of source A, and similarly for source B. This is our diluter, a very weak tunneling bridge. The tunneling amplitude is TA here and TB here. This gives rise to a dilute beam of particles whose distribution function is very far from equilibrium. The beam from here and the beam from here follow the chiral mode, the chiral edge mode on this side and on this side. The two beams meet here at the central QPC. This is our collider with a tunneling amplitude T. So as a caricature, we have for this bipartite system two particles. These two particles coming from source A and source B collide. They may be collected in the drain on the side A and the drain on the side B. And due to their collision, they may become entanglement. And the question is how to define an entanglement witness here, entanglement pointer here, and how to quantify it here. So when it comes to defining entanglement or entanglement pointer, we want this quantity to satisfy at least three conditions. The first condition is that it should be finite when the two sources this source here and this source here are on, so that the beams coming from here and coming from here talk to each other. We want a quantity that will be 0 when only one of the sources is on and the other is deactivated. Second condition, we want this quantity we define to represent statistical information of the quasi-particles involved. And thirdly, we want this quantity to be made of building blocks which are experimentally available. For example, the building blocks should be currents or current correlations or noise. And in trying to define these quantities, we need to face 3 enemies. And now I'm going to list these 3 enemies that we want to be very careful of. The first enemy has to do with beam partitioning entanglements. What I mean is the following. This is a tourist view of our system. And let me now deactivate source B. So I have only source A. Source A gives rise to a beam. A small part of it tunnels to this chiral channel and eventually arrives at this QPC. As a function of that, as a result of that, some of the particles will arrive towards in the drain of A, some will arrive in the drain of B, and one can show easily that the current correlations between the current here, IA and IB, is non-zero, is a non-trivial quantity. Nevertheless, this is not what we want, because here there is nothing that gets entangled with these particles. So such contributions of current correlations that arise from the presence of a single source are redundant contributions. We should get rid of these guys. We need to get rid of such cross-current correlations. The second enemy has to do with classical entanglement. So this is the famous story of the blue shoe and the red shoe. I take 2 shoes, put them in closed box. I give 1 box to the chairman here, and I keep 1 box here. And I open my box. I see that I have the blue shoe, and immediately I know that you have the red shoe. So this system of the 2 shoes can be thought of as classically entangled, but of course one cannot perform rotations in the red-blue space. We cannot perform Bell measurements. So this is not really an interesting or sophisticated quantum entanglement. So how this classical entanglement appears in our case? Let me take a caricature where I have 1 particle arriving from source A and 1 particle arriving at source B. These are identical particles, but nevertheless, I denote them as the red particle and blue particle, just for pedagogical reasons. So these 2 particles, this particle can proceed here straight or tunnel here. Once it tunnels here, it can proceed straight to DB or to the collider, and similarly this one. So let me now enumerate or list all the possible outgoing states. And of course, in general, the outgoing state will be a superposition of these components. So here they are. I can end up with the two particles going to a part A of the system. I will call this state psi to 0. Two particles end up here, 0 particles and in B. So the particle that came from here went straight, and the particle that came from here tunneled here, and then tunneled here, and end up here. Similarly, I have psi 02. I can also end up with one particle showing up in A, and one particle showing up in B. So the particle showing up in A will be in the superposition of this mode and the other mode, and I denoted this component as blue and red to show that due to the collision here, there may be some amplitude coming from the originally injected particle here. So these states, 1, 1, can have a given phase, similarly this component, and all in all, I can show that there are two orthogonal, possible orthogonal states, which are 1, 1. I will call one of these states 1, 1 alpha, and the other 1, 1 beta. So now I can write down the entire outgoing state as a sum of two components, psi c for classical and psi q for quantum. So the classical one will be a superposition of these two components. Why do I call them classical? Because if I think of these particles as fermions, the fact that I have one fermion here and one fermion here, and recalling the Pauli blockade, I cannot perform any rotation in the space A. And similarly, I cannot perform any rotation in the space B. So these are the analogs of the red shoe and the blue shoe. Now, they are classically entangled because if I find that there are two particles here, I know for sure that there are 0 particles here, and vice versa. If there are 2 particles here, I know for sure that there are 0 particles here, but I cannot perform any rotation, any Bell measurements. By contrast, this component is quantum because I can perform a rotation separately in the space of A and the space of B.
Yuval, yeah. Can we say that this classical entanglement for you is just a way to say that you can always have a perfectly separable state in the split state? Is this equivalent?
As a result, yeah. As a result, yes, yeah. So the third enemy has to do with entanglement, which is generated by interaction, conventional electron-electron interaction. And the interaction can show up in 2 ways. Inside the collider, the central QPC, or if we have several parallel modes, edge modes, it may be due to interaction among the edge modes, which leads to a so-called charge fractionalization. I don't have time here to explain it, but this is a very fascinating issue. So we have two contributions to the entanglement. So let's try to assess how important interaction is in an experiment. And here I'm showing you an experiment of electronic platform. So I show here the cross-current correlation, the current IA, current IB. This is this panel denotes the results when the 2 sources are activated. This shows the result when only source A is activated. TA and TB is the degree of dilution here. And what you can see is that the red curve, which denotes the theoretical expectation in the absence of interaction, and the blue curve which shows the actual experiment with interaction differ from each other quite significantly, both when two sources are on and one source is on. So interaction is important in this system. And the challenge is that we want to get rid of that, because interaction is a non-universal entry, affects our entanglement entropy in a non-universal way. And we are after the entanglement entropy, which is due to statistics, due to something universal. And so this is our definition of our entanglement pointer. It is the irreducible cross-current correlation when both sources are on, minus the one when only source B is on, minus the one when only source A is on. This is a definition. Let's see how successful it is. First of all, it is zero when only one source is on by construction. Secondly, theoretically, if we don't have interactions, the value of this entanglement pointer will give us zero or positive or negative, depending on whether we have distinguishable classical particles or fermions and bosons. So it is qualitatively different between particles of different statistics. This is to be compared with the bunching probability when we inject one particle from A, one particle from B, which may also give us this information, but it's less universal, more problematic when we come to the case of anyons. So at least it gives us some qualitative information about the statistical nature of the particles involved. Now, let's see how this entanglement pointer appears in experiment. So this is the experiment on an electronic platform. The red curve is the prediction in the absence of interaction. The blue one is the prediction with interaction. And you can see that the difference is quite small. To put it more quantitatively, this is our entanglement pointer. It is some combination of the tunneling amplitude of the central QPC and the tunneling amplitude of the diluters. The prefactor 2 is the prefactor in the absence of interaction. This 2 is corrected by a factor which is due to interaction. And the interaction comes from fractionalization and interaction with the QPC. And experimentally, it turns out that this P interaction assumes the value of 0.08 compared with 2, so it's a 4% correction. And the big success is that the interaction correction is not first order in the dilution, but turns out to be second order in the dilution. So it's pretty small. Yeah. Next, we can try to, from the entanglement pointer, go to the entanglement entropy, or something I call SEE, statistics-induced entanglement entropy. And this is the definition of the statistic-induced entanglement entropy. This is will be the entanglement entropy, the total entanglement entropy, where both sources are on, minus when source A is on, minus when source B is on. And it turns out that this is equal to the entanglement pointer times this logarithmic factor of the tunneling amplitudes involved. So once we have the entanglement pointer, we can write down the statistics induced entanglement entropy for the electronic platform. And the features of this statistic-induced entanglement entropy is that it is only non-zero when both sources are on, and when the particles involved are indistinguishable. It represents the entanglement entropy that is generated purely from statistics, and it is experimentally available. So,
I have another question. I mean, is this positive definite?
Is this?
It's positive definite?
Yes. All these factors are smaller than 1. And all these factors are smaller than 1. So here is the experiment. You can see the theoretical value of this statistics-induced entanglement entropy. This is the red line. This is the blue line. Interactions give us some correction, but this correction is small. So it's a pretty good fit, and there is only minor influence by the interaction. So having said that, so this is the first experimental measurement of entanglement entropy in transport system. So having said that, let's move now to anionic platforms. And the specific anionic platform we're going to discuss here is the so-called Andreev-like anionic platform, and I'll explain it. And if you ask me why I chose this one, I'll answer this question at the end of my talk. So this is our setup. The white screen here represents a fractional quantum Hall condensate, for example, nu equals 1/3. The black areas are gate-depleted areas. These are mountains in this incompressible sea. And next to the mountains, there are chiral edges, for example, a single chiral edge in the case of nu equals 1/3. These are tunneling bridges, TA and TB, that allow tunneling of anyons. And here in the middle, I have a relatively large barrier which depletes the electron gas, and therefore it allows tunneling, but only tunneling of electrons from one side to the other. It does not allow tunneling of anyons. So let's zoom on this central part and see what happens when we inject a single anion, a single wave packet whose charge is nu e, for example, 1/3 of e. This guy can proceed straight without tunneling, but if tunneling event should take place, as I said, only electron can tunnel from this side to the other side. So we end up with electron here, but in order to conserve charge, this 1/3 continues as a whole of 2/3, as a whole of nu minus 1 times e in general. So this is the case when a single source is on. When two sources are on, we'll have an anion coming here on the red, whose charge is nu e, 1/3 e, for example. Another one, nu e. And let's say that electron tunneled from here to here. We end up with an outgoing wave packet whose charge is the original charge of this guy plus an electron, nu plus 1, 4/3 e. And here we'll have a hole of minus 2/3, and vice versa if the tunneling occurs in the other, on the other side. So the question is, having this anionic Andreev-like tunneling, by how much the outcome of this collision differs from when we take only one source and then take only the second source and add up the results. To what extent the fact that there are real two sources active at the same time, sort of Andreev collisions, to what extent this matters? And the result of the calculation is that it does matter, and similarly to what we did before we can construct an entanglement pointer. And the entanglement pointer, the expression for the entanglement pointer is shown here. I plus here is the sum of the incoming current from here and from here, the incoming current into the collider. S here is the electric noise of the current through this bridge. So this is the noise when only source A is active, the noise when only source B is active, minus the noise when both sources are active, and these quantities are measurable. So let me now open a bracket, a big bracket, and I'm going to spend the next 3 minutes on something technical. If you don't want it, just switch off and wait till I close this bracket. But I'm going to give you the flavor of what kind of calculations are involved here. So the contribution I'm going to demonstrate here is a contribution when one source is active. But of course, we need to take also contributions when two sources are active. So this is our platform. Because only source A is active, I omitted the other chiral here, which is the chiral coming from source B. So I have 3 chirals. This is the diluter. This is the central QPC. And let me compute certain expectation value. Omega is the vacuum, and eta will be Keldysh indices. I take Keldysh indices which are different, eta 3 and eta 4, which will appear immediately of opposite signs. So at time S1, I generated here in the diluter an anion and anion hole, anion tunnel from here to here, leaving behind an anionic hole. So these are these operators. I generated the anion at A, and I generated a hole at SA. 0 is the location of this diluter. So these guys move in, and at a later time, I generated time S3, I generated another pair. And they move on. And at a later time, which I call S2, I had another process, opposite process, where anion tunnel from here, from A to SA, leaving a hole behind at A, and the anion here. And they all move here. And then when the first pair arrives at the collider, I have an Andreev tunneling. So this is I call this time T0. Electron tunneled from this side to the other side, from A to B, leaving an electron hole here and electron here. So here I have the original anion, plus 1/3, and the electron hole, -1. All in all, I have a hole of 2/3. These guys proceed, but since I had here this Andreev tunneling, capital psi denotes electronic operators, little psi anionic operators, and if I exchange this guy with this anionic operator, I will accumulate some statistical phase, which turns out to be a pi. So these guys now continue, and at a later time, I have an opposite Andreev tunneling, leaving behind the hole here, and remember I had an ionic hole, and now after the Andreev, I have a particle which was the electron minus the anionic hole, which is 2/3. And this is the term denoted here. And again, I will need to exchange this guy with the other operators here. I'll do it immediately. But all this complicated process will now interfere, or will have a scalar product with another simple process where I generated a pair at the diluter, and this pair arrived at this point here. These are the dashed lines. So the dashed lines had to exchange positions with this anion and this anion, and the statistical phase are shown here. All in all, when I collect all the statistical phases, I have a total phase of 2 pi nu. So I'm closing now my brackets, but this is only to show you how different contributions to this correlations introduce or give rise to a statistical phase, or depend on statistical phase. So this is one way to write the entanglement pointer. But if I follow the type of calculations that I did before, I find another more universally looking expression for the entanglement pointer. It depends on capital TA, which is the square of the tunneling amplitude to diluter A, the square of the tunneling amplitude to diluter B, and the square of the tunneling amplitude to the central collider, times this universal factor, which depends on U. The denominator has to do with the fractional charge. The numerator has to do with the statistical phase. We obtain, what is interesting is that we obtain entanglement here between the anions at A and the anions at B, although only electrons were allowed to tunnel between A and B. So the electrons have introduced, the electrons with their trivial statistics, Fermi statistics, have introduced entanglement between the anionic system at A and the anionic system at B. And this is how experiment looks like. The blue is the theoretical expression for the entanglement and entropy. The red are the experimental measurements, and except for a very small range of current bias, the fit is not bad at all. So this is what I wanted to convey to you here. And from here, there is a long list of things, challenges that are interesting to tackle. Let me mention 2 of these challenges. One is to replace my Andreev-like anionic collider, where only electrons can tunnel from A to B, by real anion collision. And the other is that when we have our entangled outcoming wave packets, which I showed before, can I manipulate this entanglement, leaving aside the classical component and doing a Bell measurement, Bell inequality measurement manipulations with the quantum components. And with this, I would like to thank you very much.
Yeah, thanks Yuval for the very nice talk. We have time for a few questions.
Okay, one second.
Hello. Thanks for nice talk. So this entanglement entropy that you are trying to experimentally verify for some particular system. So my question is, your bipartite system, which is prepared, is it a pure state? Because otherwise entanglement entropy will not be a
Is it, you're asking whether this is a pure state?
Bipartite system, bipartite one.
Yeah, I mean, the outcoming waves in any given, let's divide it. Suppose I first take a caricature. I have one particle coming from here, one particle coming from here. And then they either collide in the case of electrons, or they have all these anion, anti-anion generations that I showed before. This is a pure state, which is the same pure state when I started introducing entanglement entropy. The entire, I assume that the entire density matrix of the entire system is pure. It becomes mixed only if I traced out part B. Now, if I have a whole beam, which is the more realistic, then it will still be a pure state, but of a exceedingly large Hilbert space, high-dimensional Hilbert space. And I don't want to deal with, I mean, I cannot even deal with this. I need to find something more smarter to do.
Thank you.
Yeah. Hi, I had a couple of questions. So the first one is, if you just have pure states, then if the state is separable, then there would be no classical correlations, right?
So if this is a pure state, then?
And if the state is separable, then it would just be a product state. Like, so there would be no classical correlations too. So what would be the notion of classical entanglement?
Right. So as I said, the entire outgoing wave consists of different components. It's superposition. And when I have many particles, it's a very complicated superposition. So in order to get the sense of a classical component, let me assume that the beam, the incoming beam, is very dilute. So I can analyze it, particle by particle. So there is a chance that those separate wave packets arrive at the collider separately. They don't even overlap. Let me talk about electrons. It's easier. With anions, it's more complicated. So here I have this electron coming here. It will split to A and B as if there was a single source. And then comes another one from B, splitting into A and B. And all these contributions, when the wave packets arrive separately and they are not aware of another wave packet, will be subtracted out by the way I define my entanglement pointer. I define my entanglement pointer as two sources on minus one source on minus second source on. It's only when the two wave packets overlap or partially overlap that they are aware of each other. Now, when they are aware of each other, I can end up with the two particles ending up in part A, or the two particles ending up in part B. In that case, the system are separable. And that will be the analog of my classical entanglement. Only when one particle goes to part A and one goes to part B, then these components know about each other through the statistics of the particles.
Yeah. And the second question was, conceptually, is an entanglement pointer identical to an entanglement witness?
Entanglement pointer is identical to entanglement.
Is it exactly the same as entanglement witnesses, or is it slightly different?
There are various entanglement witnesses in the literature, so I don't want to say that it's identical. This is a very special system with quantum transport, but it's what you can show that it is a monotone of the entanglement. Now, one very justifiable critique of what I show here is that I give you some quantity which is an entanglement. I connect it to the statistics induced entanglement entropy. But I did not yet perform Bell manipulations or CHSH manipulation. And this is our next, I mean, we know how to do that, but this is not yet done. So it falls short of doing this Bell equality.
Thank you.
Yuval, thanks for a very nice talk. I understand that in your setup, you have anions on the left and then anions on the right, and the tunneling is actually through electrons, and so, yeah. But I was just wondering, if I just have one anion gas, or, a bunch of anions, all right, is there a way for me to construct a local Hilbert space and talk about entanglement in the usual way people talk about entanglement by tracing over? Is a local Hilbert space description? Here I understand it's possible on the left and on the right. But suppose I had one anion gas and I had this question whether it's something.
So let me see that I understand you. You are saying, forget about collider. I just have a dilute beam. Can I mean, the dilute beam extends over a very large chiral mode with all kinds of wave packets. Can I take this as my system and then trace out part of the system and ask whether this part is entangled with the other part? My answer has three parts. First of all, this has not been done. It's a very relevant question. It has not been done. Secondly, what we have done, we were very recently looking at this gas, dilute gas of anions, and try to characterize it by an effective chemical potential, an effective temperature. And it turns out that this characterization is very different from the one that you will do or you will obtain for a dilute non-interacting fermion gas. And we suspect that these differences are exactly because of the long rangeness of the anions. I mean, even if you have an anion wave packet, something far away knows about it. And there are all kinds of indirect circumstances. The third one is a sort of a warning. I would, when I do that, I suppose I manage to do what you recommend me to do. I have a wave packet, some other wave packets far away. I want to integrate this. It may very well be that the entanglement entropy that I will obtain, the non-zero entanglement entropy, will not be due to statistics, but due to the fact that I have just long-range correlations due to interaction. So I'm not sure that I will know how to distinguish between them. But this is a very relevant question.
I mean, non-interacting electrons in like many particle non-interacting systems, there you can, like for pure states, one can show that the entanglement is directly related to number fluctuations, right? Like use this full counting statistics. So is your definition here of entanglement in this interacting is kind of motivated by that, like by the what one has for non-interacting electrons?
So let me repeat. You're asking whether the way I define it is related to other attempts to talk about number statistics or number fluctuations. Okay, so there is a very well-known and very fundamental paper by Levitov and Clich for electrons. So I have a one-dimensional platform, non-chiral. I have a beam of electrons, and then I have a barrier, Landauer type barrier. So the impinging electrons in part are transmitted, in part are reflected. And let's say that I do my experiment over a given time, and I have n impinging electrons, and I can ask what is the full counting statistics of the number of transmitted electrons. And what they've shown is that if I have the full counting statistics, which in other words means that I have all possible infinite series of cumulants, I can calculate the entanglement entropy of this system. So this will be your number statistics. This, any experimentalist will tell you, is highly impractical. If you tell experimentalists to do that, they will be scared of. So the way we are, the triumph here is that by looking only at second moments, I mean, average currents, first moment and second moments, we were able to obtain a measure of this entanglement entropy. So I think it's different from the full counting statistics.
So, sorry, you had said something like classical entanglement in quote marks. I was a little bit confused because there are classical correlations, but entanglement is taken to be that part of correlations which cannot be explained classically, which involves quantum mechanics. Is that a different terminology?
No, look, you are absolutely right. I mean, I don't want to go into language. If you don't like, if you think that the term classical entanglement is self-contradictory, you are absolutely right. I don't want to insist. But in the same way that my red shoe, blue shoe is not really entanglement. But if you are ignorant or stupid and you see this hocus pocus, you know, I mean, I open my shoe and in no time, I know exactly what the other shoe, not even the time it takes light to propagate from me to the other guy, then I would pretend that it's, I could pretend it's entanglement, but we know that it's not, that I'm cheating. So that's cheating.
Questions? Are there any extremely pressing questions? If not, do catch Yuval throughout the meeting. So with that, let's thank